Hello, everyone. Today we're going to be talking about the Standard Model, which is the theory of the fundamental forces and the particles that make up everything in the universe. Let's begin. Start off with, we're going to be talking about the four fundamental forces, which we have the strong nuclear force, we have the electromagnetic force, we have the weak force, and we have gravitational force. I'm going to be going over each of these in more detail. First off, we have the strong nuclear force. This is the strongest force. It's well named in that respect. Its goal is to hold together the nucleus, which is the protons and the neutrons. Now, you might have been thinking back from chemistry, how are all these protons being shoved in such a small place in the nucleus if they repel each other so much? Well, that's where the strong force comes in. It's considerably stronger than that force that wants to divide those protons, and that's what holds together the nucleus. So it's the force behind all nuclear reactions that we talked about in the last video. So behind nuclear power plants, bombs, behind the energy of the sun, all operates based off of the strong force. Now, if the strong force is so strong, why don't we see it in our everyday lives? Well, that's because the strong force only works off incredibly small ranges. The ranges happen to be the exact size of the nucleus of most atoms. So they only work at that atomic, very, very small level. Anything bigger, and the force is no longer there. You will often see it just referred to as the strong force, if not the strong nuclear force. The electromagnetic force is the next strongest force that we have. It's 100 times weaker than the strong force. However, it is still quite noticeable. One notable thing about the electromagnetic force is it can attract or repel. The strong force only attracts, only pulls together things, where the electromagnetic force can attract, which we see between protons and electrons, but it can also repel, as we see between electrons and electrons. It's a thing that holds together atoms and molecules. It's the fundamental force behind bonding. Its range is infinite, unlike the strong force, which is very short, and it works off of a 1/r² relationship, which we saw with gravity as well back near the start of the year. The weak nuclear force is the one that we're going to talk about least. We just have to know the fact that is 10 to the 13 times weaker than the strong force. It's responsible for reactivity. It can attract or repel. It allows fusion of hydrogen, and it also operates off of extremely short ranges, only within the nucleus as well. We're not going to get into too much detail about it. That's pretty much all that we have to know. And finally, we have gravity, which is the one that we've learned about most throughout the year. It is in a very, very, very weak force, 10 to the 38 times weaker than the strong force. Now, this is the one that we're most familiar with and we see on an everyday basis, so we imagine it being very strong. But keep in mind, the mere act of picking up something like a book, or right now I'm picking up my phone, I'm overcoming all of the force that planet Earth is pulling on this. So that is how weak the gravitational force is. Though Earth is constantly pulling you down with this force, you can easily overcome it yourself. It is only attractive, and it controls the movements of very large objects like stars, planets, and galaxies. Its range is also infinite. Now the question is, why doesn't the electromagnetic force do all this controlling of these large bodies? Why is something so strong not really noticeable while gravity is? Well, that's because the electromagnetic force often balances itself out. If you have an even amount of positive and negatively charged objects inside a body, then you won't see any noticeable electromagnetic forces between them. So gravity is strong in the respect that its range is infinite and it's only attractive and has no repulsion to it. So it is the thing that dictates the movements of these very large objects because of that fact, where the electromagnetic force often fights with itself if it's attractive and repulsive, which is why it does not actually dictate any sort of movement. Now, on this next slide, I just have a quick comment. You can pause the YouTube video if you want to kind of comic to read it. It's just a little joke about the fundamental forces. Feel free to read it at your own leisure. Now, let's talk about the nucleus itself. So the nucleus is comprised up of our protons and neutrons, except for hydrogen, which can have no neutrons. All the positive charge of an atom is found within the nucleus, and same with most of the mass of the atom is found within the nucleus. So, yeah, basically most of the stuff going on with the atom is there, while the electrons are what's found on the outside. Now, keep in mind that the protons inside the nucleus repel each other because of the electrostatic force, but the strong nuclear force still holds them together. So that's the basic idea behind the nucleus, and how the strong nuclear force is very important in allowing those to form. We're going to be moving into the classification of matter, which is the different types of matter that we have. Now, this slide comes from the reference table. However, I just added a couple of little notes to the sides, so feel free to take out your own reference table and take a peek at what it looks like. So, matter is divided up into two categories. We have the hadrons and we have the leptons. Leptons are things that are fundamental, which means they cannot be broken down anymore. A electron is an example of a lepton. Then we have the hadrons, which are made up of these things called quarks. There's two categories of hadrons. We have the baryons, which are made up of 3 quarks. Those are the type of matter that we're most used to. That's our protons and neutrons. And then we also have mesons, which are very unstable. They don't last very long, and they're made up of a quark and an antiquark. Now, antiquark just comes from antimatter, so it's just the opposite of a quark. Now we're going to be taking a closer look on what quarks are. So we have 6 different types of quarks, and they're just defined as the building blocks of our hadrons. So we have up, down, charm, strange, top, bottom. Now, up and down were the first ones discovered, and they're the building blocks of the matter that we know, neutrons and protons. While the other 4 are more unusual and only make up very strange particles that often do not exist for a very long time. I'm talking about in nanoseconds or even less amounts of time. So they took a bit longer to discover. Now, they all have an interesting naming characteristic. As you can tell, they're all opposites of each other. Charm and strange are a little bit odd. And top, bottom as well. In fact, top, bottom was originally called truth and beauty, which was named from a scientist who first discovered them and was kind of an interesting character. Eventually, the scientific community was like, okay, truth and beauty, that's a little bit too strange. We'll keep the T and the B, but switch it to top and bottom to be opposites of each other. Charm and strange are named that way. Strange was actually named first because it was so strange at the time. It was the only other quark discovered, and then they just put charm as the opposite of that. So those are our types of quarks. Next, we have our types of leptons. If you remember, leptons are our fundamental particles like electrons. We have 2 other types of leptons here, muons and tauons. Really not much to say about them other than the fact that you can notice they're all negatively charged, and they're fundamental as in they don't break down. At the bottom of that, we have their neutrinos. Neutrinos are very, 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 very tiny particles. And they are just often byproducts of a lot of nuclear reactions to help keep the mass charge and some other properties balanced out that need to be balanced out. Now, one thing I do want to point out for the quarks is you'll notice that they have very strange charges. They have the 2/3 and 1/3 charge. Now, if you remember, our hadrons are comprised up of different amount of matter, and in all cases, our hadrons will have a charge of a whole number or 0. And we'll see how that works out in just a moment. Now, I do want to note that every particle does have its antiparticle equivalent, which just means that it has the same mass, same properties all the way around, except for one thing, they have the opposite charge. To make something appear as an antiparticle, we put a line above it. For example, we have an anti-up particle over here. The normal symbol for an up is a U. To make it an anti-up particle, we just put the U with the little dash on it. So if we're looking at a basic atom here, we have the neutron. The neutron is made up of up and down quarks, just like the proton. However, neutron we know has a charge of 0. So what we have here is an up quark, which has a plus 2/3, a down quark, which has a minus 1/3, and a second down quark that has a minus 1/3. If we were to add up all of those together, we would see we get a charge of 0. Protons work very similar, except it has 2 up quarks. So we have plus 2/3, plus 2/3, minus 1/3. And if we add those all up, we get a plus 1 charge, which is what a proton is known for. And finally, we have our electrons at the top, which are just leptons, which means they are fundamental. They don't actually get broken down into anything else, and they have that -1 charge. If you guys remember from the last video, I talked about the fact that antineutrons can exist even if they both have 0 charges. Well, an antineutron would just be made up of antiquarks. They would have a plus 1/3, plus 1/3, minus 2/3 charge. Still adds up to 0, but they're considered antiparticles. They would annihilate other neutrons. Keep in mind that our neutron proton are hadrons, they're baryons. So, particle accelerators. Now, most of the standard model in particle physics is done in particle accelerators. And what we do how a particle accelerator works is that we take common particles like protons or electrons and we accelerate them at very high speeds. We give them a whole bunch of energy. When they eventually collide into each other, all that energy that they are made up of will start turning into other types of matter. Using the same E = mc squared, just backwards this time, we're taking this kinetic energy, these really fast particles, and by smashing them into each other, we can get some of that energy to turn into particles. Now, we study these particles, see what comes up, see if we can discover any of the properties. Most of these particles, like I said, are very short-lived, don't even last a nanosecond at a time, so we have to have very fancy equipment to do that. Our particle accelerators, the best ones, tend to be very large. In this case, we have a picture of a 4-mile long or 4-mile circumference particle accelerator. You can have one, the most famous one would be CERN, which actually covers more than 2 countries in its size, and they're planning on making even a bigger one. Now, though this seemed very quick, and we haven't really done that many examples, the standard model is a very easy concept to get in terms of what you need to know for the regions. The thing is, you just need to focus on what type of matter something is, what type of charges it has, and how quarks add up to our particles. So what we have over here is we have on the left side a list of our quarks. Then I'm asking for the type of matter and for the charge of that matter. So what I'm asking for is baryon or meson. Remember, baryon, if we look at a reference table, are the things made up of 3 quarks, while meson is made up of a quark and an antiquark. So each of these are baryon, meson, baryon, and a baryon. Yes, this is an antibaryon, but it is still considered a baryon. Now, if we were to add up the charges, again, we would want to look at the reference table to find all of them. A charm and a top quark both have plus 2/3, while a strange has a minus 1/3. So we have a plus 1 charge. An up has a plus 2/3, and anti-down has a plus 1/3. Keep in mind, if we have that dash above it, that means we're taking the opposite of that charge, so plus 1. And you guys can go across and try these out, but these are the answers right here. Take a look at the reference table, see how they fit together. In your own words, compare and contrast the 4 fundamental forces. So just look at the slides, take a peek, try to look at the differences and similarities between them. Think of things like their overall strengths. Think of things like their ranges, stuff like that, attractive, repulsive, things like that. Have a good one.